Okay, so we're going to talk about the last section in Unit 3. This is exponential growth and decay. And this is going to sound familiar because it is exponential growth and decay, and so you learned that in secondary 3. Technically, most of this information could be solved without calculus, but I do integrate every time just to make sure, and so I do use calculus on mine. But you are welcome to memorize some of this information to help you save time. So consider the statement. It says the rate of change of some quantity is directly proportional to its current value. So rate of change implies a derivative, and directly proportional, that's something you would have learned before this class. We've not seen that, but that means to multiply by some unknown constant to its current value. All right, and so we're going to set that up as a differential equation. So we're going to let the quantity be P. The rate of change of some quantity would be dP dt, and directly proportional means to P means K times P. All right. So if we set that up as an equation, that statement, we would have dP dt equals K times P. And that's a differential equation because it's a derivative. So if we wanted to solve that, that's what we did in the last section. So this is not new or even difficult, but this is the reason why I went through some of that notation with you so we could get it in an exponential form at the end. All right. So we integrate both sides. We've got the natural log of absolute value. Set up your exponential equation. We're going to use the exponent properties to separate them. We've got our unknown constant because e to the c is also a constant. And then we would end up with this exponential form. Remember, it was like a b to the x. Exponential growth means our base is e. And then if our k was bigger than 1, less than 1, then we knew we were growing or decaying. So some students do just memorize the final step. For me, it really doesn't take me that long to go through all of the steps, and so I just don't memorize it. It's completely a choice, all right? There is one situation that might come up, and you would have to just integrate this by hand as well, and it would be if it said it was inversely proportional. This doesn't happen a lot, but inversely proportional means your derivative is equal to k divided by x instead of k times x, all right? And so then you would separate, integrate, everything else like that. So, like I said, we are decaying if our k is less than 0. We are growing if our k is greater than 0, all right? And it's really not for us to determine that. We can find the information. So that's not what they're going to ask you to do. So there's two things that they will ask. It will ask you either to set up a differential equation or to actually solve. Okay, so we're going to practice both of those. On scenario number 1, if they don't give you variables to use, then you're going to define your own variables on a free response question. So it says the rate of change of the area. Rate of change implies the derivative of area. So I'm going to let A equal area. Over time, that means time is our variable, is proportional. So I'm thinking K times product means to multiply of its radius and the rate of change of the radius. So I'm going to let R equal, radius. So now we need to write this as an equation. So I just go in order. It says the rate of change of the area. So we can write that as dA dt. That's all of this. Is implies equals. Proportional means I'm going to multiply. The product, I'm going to multiply something else, of the radius and the rate of change of its radius. Now, a derivative is always with respect to time. Now, there's a lot of unknown here, but that's not for us to solve. It was just for you to set up. So that question is done. Let's try another one. The rate of growth of a population is proportional to its product of its current population. They let that be P, and the difference between the current population and the maximum population. All right. So they are letting P be our population. So the rate of growth of the population is dP dt. They don't say over time, but it's always implied. Is proportional means to multiply to the product of its current population P and the difference means to subtract. And when you see the word difference, it means you're going to take that subtraction in order. So the current population and the maximum population. Now, that will obviously end up with a negative value, and so that does mean something in terms of growth and decay, but once again, that's not for you to solve, okay? All right, example number 2 has a couple of parts, and so if you look at the answers, this does imply that we're going to use a graphing calculator, and we're going to solve this. So, water flows continuously from a large tank at a rate that's proportional to the amount of water remaining in the tank, and they give you this formula, okay? So if there's initially 10,000 cubic feet, that means that 0, 10,000 is an initial value in the tank, and at time t equals 4, we have 8,000. That's another condition, known value, I won't say initial. Feet remained. So it says, what is the value of k in this equation? All right. So our function is y, and our variable is t. So we've got t, y, t, and y. All right. Once again, this is in exponential form, and we skip straight to it, but I don't. So first, before I integrate, we're going to do just what we did in section 9.2. We want to separate the variables. So I'm going to divide by y, multiply by dt. I'm sorry, not k. I need a k. Remember, k is a number. That's what we're solving for. So we're going to integrate. We get the natural log of y is equal to kt plus c. So now at this point, I'm going to use my first initial condition to try to get rid of one of these variables. So I know that t equals 0 and y equals 10,000. So we get the natural log of 10,000 is equal to 0 plus c, so that's our c value. Okay, so I'm going to write that over here. I get natural log of y. And I keep the bars on it because we do have another condition, kt, and then that's my c. So plus natural log of 10,000. Well, we need to find k. So now I know another value. I know t is 4 and y is 8,000. So natural log of 8,000 is equal to 4k plus natural log of 10,000. And so you notice all we have left is k, so we can solve for this. I'm going to subtract 10,000, so natural log of 8,000. You're not allowed just to subtract 8 and 10,000 because they're inside the log. Now, we are allowed to use a graphing calculator, so if you didn't remember, this is a quotient property, you don't have to. You can just type those in, and then we'll divide by 4. Make sure you use a parenthesis, okay? But as a review, remember when we subtract two logs, that really can be written as the natural log of 8,000 divided by 10,000 divided by 4, which does reduce a lot. So what's that, 4/5? It's really a choice. So let's go ahead and type that in and see what we get. So natural log, I am going to use my reduced. 4 divided by 5, and then divided by 4. So I got negative 0.055785. Okay, so they went to 3, 0.56. Okay, and so that's our k value. So then we know natural log of y is equal to, we know that that's k now, so I always like to use more decimal places if I'm not at the end of the problem. So 0, 5, 5, 7, 8, 5, kt plus natural log of 10,000. Okay, so I'm just going right here. That's my equation. So to the nearest cubic foot, how much water remained in the tank at time t equals 8? So we're going to go ahead. I've got natural log of y is equal to, I'll go ahead and just type that in. And since we're in the middle of a problem, I really do use all the decimal places that I can. 785 times 8 plus natural log of 10,000. I could have cleaned this up, but really if you get to use a calculator, go for it. 8.764060372. At this point, now I need to solve for y, so e to that power. So e to this equal to, it is the absolute value of y, but all these conditions tell us it's just going to be y because it's the positive roots. So we'll go ahead and type that in. 8.764060372. So I got 6,400.045. So, and it said to the nearest cubic foot. Okay. So that's kind of how we can use separable differential equations with exponential growth. All right. Let's try a third example. So this says the rate of growth of the volume of a sphere is proportional to its volume. So I need to write that in a differential equation. The rate of growth of the volume is dv dt is proportional to its volume. Okay, so V equals volume. If the volume of the sphere is initially 36 pi, so I know 0, 36 pi, and expands to 90 pi after 1 second, find the volume after 3 seconds. Okay. So once again, we're going to separate, integrate, plug in some initial conditions, and find what they need. So let's go ahead and separate. I'm going to divide by V, multiply by dt. We'll integrate both sides. So the natural log of V, and because we're talking about volumes, these are going to be positive, so it's okay if we leave that bar off. I just don't like to. So kt plus c. Just remember, t is our variable, and these are our volumes. So I'm going to go ahead and use my first initial condition. So if t is 0 and v is 36 pi, we get the natural log of 36 pi is equal to 0 plus c. Okay. So natural log of v is equal to kt plus natural log of 36 pi. Then I want to use my second condition. So I know t equals 1, and my volume is 90 pi. So natural log of 90 pi is equal to k plus natural log of 36 pi. So subtract natural log of 90 minus natural log of 36. Remember, I can't just subtract those. What I actually can do, and I'm going to do it, is put them together with the quotient property so we can divide them. Okay, because it just looks a lot easier for me to type in. So the pi's reduced, both of these divide by 9. What's that? 10 and 4 divide by 2, so 5, 2. So k equals the natural log of 5 divided by 2. I'm even going to write it as 2.5. So plug it back into our equation, which was in red. We have the natural log of v is equal to kt. So natural log of 2.5 t plus natural log of 36 pi. And what do they want? They want to know the volume when t equals 3. So if t equals 3, then we can solve for v. And I don't solve for v before I plug that in. It's really a choice. I get this times 3. So remember, we're going to type all of this straight in. It's not 3 times 2.5. So natural log of 2.5 times 3 plus natural log of 36 pi gives me 7.477121002. And then we need to solve. So we're going to change this into an exponential. So e to that, use as many as you can, equals v. So 1767.146. And what was this in? Cubic feet. Okay. All right, that's the idea. So on your practice, I give you a bunch of multiple choice questions, and you can put all of your answers in the purple boxes. There are 5 questions for you to try. All right, so good luck.